Most people go through life not thinking about or considering cables. And come on, why would you? But just imagine for a second a life without cables. No internet, no kettle, potentially no heating, and no cups of tea. They can be in hard to reach places or hidden away in walls and structures. There are lots of considerations for an electrician when it comes to cables. Come with me on my journey in learning to become an electrician, and this week we'll have answered why electricians charge so much, and I promise that you'll understand a little better by the end of this. As a trainee electrician, I've been considering everything I need to know to install, repair and make additions to electrical circuits. If you haven't worked out by now, it's getting all the renewables on the network that interests me. How about a video series explaining each element of the evolving electrical grid? Let me know in the comments if you'd like to see that. This week I delve into why the job of an electrician isn't as simple as bashing in 2.5mm cable for rings and 10mm for showers.
Yeah, it's getting late. Just get that 2.5mm off the van, that'll do.
We've talked about cables before, but just to build on what we've talked about, like jeans and trainers is the go-to outfit, the standard run-of-the-mill PVC flat twin and earth is the general go-to cable, and we'll get back to PVC cables later. But we have some specialist cables like MICC cable for high temperature environments and SY cable, a sort of flexible armoured cable. A large part of the selection process of choosing a cable is the environment, as well as the current the cable is to carry in normal operating conditions and fault conditions. This of course can be affected by the environment. Will the cable be in the sun? Will it be at risk of damage? What will the temperatures be? Another key consideration is voltage drop, but we'll get back to this later too. Okay, so step one before an electrician even chooses a cable for the circuit, they've got to work out how much current the circuit design will require. Okay, let's start with an example and then we'll follow that through. Let's say we've got 8 fluorescent tubes.
Why would you have 8 fluorescent tubes? It's 2024.
Anyway, you'll find out in a bit. I wanted to make a point. We want to work out the design current, the IB. We quite simply times the wattage of each lamp by the number of lamps to get the total power for all of the circuit. But then we need to add a correction factor because of the additional current caused by the lagging power factor of this type of bulb. Okay, I know a fluorescent tube could be a bad example for a circuit because we just don't have much use for these anymore with LED lighting. But it's good to highlight the correction factor that we would need to take into account. The correction factor in this case is 1.8. So we times the power of all of these bulbs by 1.8 and then divide it by the voltage to give us the total current that the circuit could demand if all the lights were to be on. And that comes to 5.32 amps. I'm slightly going off topic here, but these lamps nicely highlight how behind the times they are. And there are still many of these installed. 8 LED bulbs of roughly the same lumen output would draw around 1 amp-ish, around that sort of figure. And there's no correction factor for these. In addition to no flickering, being able to be dimmed, no mercury, easy to control as they work well with systems that smartly control lighting, where they can be turned on and off many times through a day. They have a much longer lifespan too, which is useful. It's a bit of a no-brainer really for anybody that has fluorescent tubes to give these an upgrade. Anyway, back to the example. Finally, before we move on, diversity is something that would need to be taken into account when deciding what the design current is of the circuit. This is where we consider devices such as cookers. We don't expect all of the cooker rings and the oven to be on at the same time and be drawing the same amount of current. So we calculate the amount of current that we'd expect based on that. The next step is to find a protective device that can work with our design current. It needs to provide protection for overloading the circuit. Not something that's likely to happen with our fluorescent tubes, but we could have an earth fault where a wire may come loose and be touching, say, the metal of a light switch. Or a short circuit where the line and neutral conductors connect. Generally, we would do this with a circuit breaker working on either the heating effect or the magnetic effect to break the circuit. A fuse is only going to rely on the heating effect, whereas a miniature circuit breaker and an RCD would rely on both of these effects, with the magnetic effect being caused by the overcurrent, which then causes the connecting contactor to be pulled away. Interesting to note that RCDs are classed as secondary or supplementary protection, and they're designed to protect people from shocks, and they're not designed to break in an overcurrent situation. So we need an MCB with a nominal rating equal or slightly higher than the design current. Remembering that our circuit would draw a maximum of 5.32 amps, so a circuit breaker rated at 6 amps would be the correct one in this case. Any lower and the device is likely to trip regularly. Any higher and it's unlikely to provide protection against overcurrent. We get into one of the reasons why electricians charge so much. They keep people safe. It's easy to think that DIY will save me a ton of money, right? But come on. This rating of 6 amps is not the overcurrent rating, but the rating that the breaker is designed to be able to handle in normal operation. Different breakers handle transient overcurrent, or in English, current spikes, differently. Our device has a fusing factor of 1.6. That would mean that it would take 9.6 amps for the device to definitely cause the breaker to operate. As you may have worked out, the time for operation of the device can depend on the current. More current will mean a faster response, and less current, or closer to the design value, then the current will need to be for a much longer amount of time before the device trips. This could be important, and I'm going to look a little bit closer at this later on. Okay, so our next step is to consider the environment that the cable will be in to make sure we have the correct size cable to fulfill our step 1 design current. We call this the tabulated value of current. I know, exciting, right? We have a whole bunch of correcting factors which we have to times together, such as the ambient temperature of the air, whether the cables are grouped, whether the cables have insulation around them, and whether the cable is buried in the ground, and so on. All of these allow us to make sure that we're choosing a cable which can handle the extra heat of the environment that it's in. If we were to just use the standard cable that we might use for every lighting situation, it might get too hot within insulated walls or bunched up with other cables that supply other circuits. So electricians calculate this tabulated value to make sure that the current is large enough to avoid thermal issues. If you were to start considering all of the tables that an electrician has to consider to provide these values from the BS7671 for all of these effects, for each one of these conditions, you start to realise there could potentially be a lot of calculations and considerations for choosing a cable. As I said at the start, the days of installing a standard size cable and that will do attitude are well and truly gone. Let's say that our fluorescent tubes are running in a hot attic and they're buried within insulation. Let's say that in summer, the attic could get up to 40 degrees temperature. This would give us a correction factor for the 70 degree thermoplastic standard PVC cable that we're going to use of 0.87 for ambient air temperature. If you want to know where to find this value, it's in BS7671 on table 4B1. Moving on to table 4D5, and we're going to use method 101, which is classed in the book as above a plasterboard ceiling covered in thermal insulation exceeding 100 mil in thickness. We can then find the correct cable. First, I'm going to divide the nominal current by the correction factor to give us our tabulated value. In this case, it would be 6.11 amps. So using this table for 4D5, we can see that a 1mm cable has to be downrated in those conditions to 10.5 amps. So this still has plenty for the lighting circuit. So this would be the cable that we'd choose. But just consider that there's so many variables for each circuit installed. Perhaps you can see that the job of an electrician isn't as simple as just whacking some cables in. This cable has to have sufficient carrying capacity, IZ, and it has to be higher than the nominal current, IN, and this has to be higher than our design current, IB. There's a few more considerations. Volt drop is a massive consideration. The regulations specify that for lighting circuits that only 3% voltage drop is allowed and 5% for all other circuits. So it's an electrician's job to make sure that the cable they're installing will meet the specs. Over time, I guess it kind of becomes second nature. If you install enough similar circuits, you're going to get to know different values. Let me know in the comments if you found this to be the case. Voltage drop is variable, and therefore it needs to be calculated. Quite simply, the cable has some resistance, and this will be affected by its cross-sectional area and the length of the cable. So a fat cable is going to have less resistance, and a longer cable is going to have more resistance. The calculation values are given to us within the regulations, but just to consider our example, our 1mm cable that has a volt drop of 44 millivolts per amp per meter. So times in our 44 by the design current, 5.32, and the length of the cable, which we're gonna say is 40 meters. We then need to take this value and divide it by 1,000 because we're counting millivolts and we want volts, don't we? This gives us 9.36 volts. And if you've noticed, this is more than is allowed. So we're gonna need to size up our cable. Our next cable up is 1.5mm, so let's go for that. Let's do the same voltage drop test on that cable to make sure that that one will be suitable. So looking at the table 4D5, the value for the 1.5mm cable is 29 millivolts per amp per meter for this cable. So let's try it with that figure. We get 6.17 volts. As you can see, just enough to be acceptable. Perfect. So it's a 1.5mm cable. That's it. Any other considerations before we start hammering cables in place? Well, we have to consider the earth fault loop. If a person was to touch a piece of metalwork made live by a faulty device, we need to be sure that the breaker is going to operate within the required time for this to work as it should. We need to know what's called the system impedance, or the ZS. We've touched on this before when we've looked at our dead and live tests, haven't we? But as a reminder, the ZS equals the ZE plus the R1 and R2. Given that this is all theoretical and we're calculating these values to find our correct cable and breaker, we can use the values from the book rather than a physical test using a test device. We haven't got to drag 40 meters of cable out and then test it with the probes, have we? We're going to want to consider 4 things. The maximum permissible earth fault loop impedance, which will cause the device to act. Our actual earth fault loop impedance, the level of fault current that will flow under earth fault conditions, and finally, the disconnection time for the chosen protective device at that level of fault current to make sure that it will act within the time that it needs to. Again, going back to the figures in the book, if we look this time at table 41.3, and I could be wrong, but I think the correct type of breaker for this situation would be a type C breaker for fluorescent tubes at 6 amp. The maximum impedance in ohms is 3.64 for our type of breaker. Okay, so how does this compare to our actual impedance? Well, let's break it down. First, we need to find our ZE. We're going to presume that we've gained this from our supplier, which we can do. So I'm going to use the maximum value for the TNCS system of 0.35 ohms, and then we'll add that to our R1 and R2. And we can get these from the book in milliohms per meter. Here, I'm gonna do something hilarious. I'm gonna switch to the on-site guide rather than BS7671, and I'm gonna go to Appendix I. Presuming that our protective conductor is 1 mil, the R1 and R2 value would be 30.2 milliohms per meter according to table I1. So let's times that by the 40, our meters, and then divide that by 1,000 because we want our ohm value, which gives us 1.2 ohm. But we haven't taken into account temperature. As temperature increases, so does resistance. So using table I2, we then have a correction factor of 1.08. And then moving on to table I3, and because we're dealing with a cable rather than a single conductor, we then have a correction factor of 1.2. So to work this out, we're going to do 30.2 times 1.08 times 1.2, and then times that by our cable length of 40, and then we're going to divide that by 1,000. So 0.039 ohms. Adding this to our ZE of 0.035, we get our calculated ZS of 0.39. And if you remember back, our maximum ZS that this breaker is to work at is 3.64 for the breaker to work in a fault situation. Our last consideration is whether the cable complies regarding thermal constraints. As we've discussed, our maximum current would be during a fault condition, so we need to turn our value into a fault current. The IFP equals our nominal system voltage to earth divided by our ZS loop impedance. So 230 divided by 0.39. 589 amps. We do need to make sure that this amount of current is going to activate the protective device in the allowed amount of time. The higher the fault, the faster the break-in time. I'm pretty sure that this will be just fine in this situation, but let's test it out, okay? Using figure 3A5 in Appendix 3 of the BS7671, back to that book, I was able to work out that the fault current is more than enough to disconnect the circuit in the required time. So our final formula, using these figures for making sure that the CPC size is greater than the minimum, is this formula.
So we square our current of 589, and then we times that by our disconnection time, which is 0.01. We then need to find the square root of this value, and then times that by the K value, which we find in table 54.3. This gives us a minimum permissible cross-sectional area of our CPC or earth of 0.51 millimeters squared.
This is well below the 1 mil that the cable needs to be. Perfect, we have our cable. And there we have it, all the calculations that we need to correctly size our cables. This would then be done for however many circuits that are being installed, so there's many calculations. Generally you'll find that companies will use software which contain all of the formulas within BS7671, for a fee of course, to make the process a little bit more simple. If you're an electrician and you've been watching this, please, I need to know what recommended software that I might use for these cable calculations. Thank you in advance. Hopefully you've understood what we've talked about today. It took me a few reads to get all of this in my head, but I have far more of an understanding now. So, why do electricians charge so much? Well, first off, hopefully you've seen there's a lot that goes into it. All of these calculations have to be done and the cables need to be correct. If it wasn't, it could all come back on the electrician. There's a lot of risk in cables not being sized correctly. People could quite simply die or houses could get burnt down. So electricians have to have a good knowledge, and they do. Running cables is only part of the job. There's a lot to consider. And there's lots of complication and understanding that goes into a job. When you start to factor in insurance, running a van, the constant need for tools to be calibrated or replaced, and materials just costing more and more each year that goes by, it's understandable that electricians need to charge their fee on top for their knowledge, experience and capabilities. I mean, as long as they're not charging artisan prices, hey?
Moolah, fat stacks, whatever you like to call it.
I hope you've enjoyed this week as much as I did. I finally got myself a scientific calculator, which came in handy this week, and I'll be using that in my upcoming science exam in a couple of weeks' time. I have a lot of revision to do before then, and then I'm back to the big books of studying. See you next time. Battery Man out.